Hello and welcome. Here we are in lecture 4. As you can see from the title of today's slide, we're going to move on from combinational logic to sequential logic, sequential circuits. By sequential, of course, we mean circuits that have state. In this case today, we mean registers. And this kind of is going to wrap up our crash course on Chisel, where after today, you're able to make Chisel components that have, combinational logic, registers that make sequential logic. You can instantiate modules, etc. So basically, most things you can do in Verilog, you could basically effectively now do in Chisel. And even though we're just starting out with this basic stuff, there's already some niceties in terms of types or parameterization you're starting to see. And the coming lectures following this will even get more in depth into the parameters and the cool things we can do. Okay, so what are we gonna do? Number one, registers, right? How do you do registers in Chisel? We're gonna cover that. We're gonna put some example sequential blocks in particular. We're going to use the example of building a counter and show it done different ways. And we'll actually have a chance to talk about different styles of coding that have functionally the same hardware. And it's just a matter of which one we find more clear, easier to write, etc. Then we'll also, of course, show the big state machines, which is a great, helpful thing to do. And then finally, I'll conclude by demonstrating a bit of the tools. In particular, when we build hardware circuits, right? The question is, when you spend all this time doing hardware design, well, what do you do for your design? Well, you, of course, can send it out to get manufactured and go through a full physical design flow and print mass and make ASICs, right? I'm not going to do that in this course. You could take the Verilog and pass it through a FPGA tool flow and push FPGA. Sure. What we actually do in this course most of the time is we actually simulate it, right? And so with simulation, of course, you have different ways you want to access it, whether it be looking at the output of a certain value, using a tester, or weaving waveforms. So we'll cover that at the end of today. Okay. So let's go ahead and load up our notebook. Great. Okay, so registers, of course, are the way you hold memory in hardware. We'll cover actual having MEMS like for SRAM in the future lecture, but for a flip-flop, this is what we have. And so Chisel, like I said, is desired to be simple. You get a synchronous positive edge triggered, D-type flip-flop. That's what you get, right? All that are exotic. Or not even so exotic, just, different types of state elements. They're not in the language by default. You use something called a Verilog black box to import one if you really want to. But it turns out in, stable digital design, you often don't necessarily need them. So this is why you get away with this. And so, yeah, you can declare a register. And so what's nice about it is that you actually are very explicit about declaring a register, right? Rather than having like you do in Verilog, where you write a always block and you write it in exactly the right way, and the CAD tools synthesize it, or they infer that you meant to have a register. In Chisel, it's very direct. You say, hey, I want a register. Boom, reg. No ambiguity, right? No question about synthesizing. Oops, I got something wrong with my always block. I got a latch around a register. No. You say you want a register, you get a register. There's a few different flavors in terms of which ports are on a register, but at the end of the day, it's still a register. And what's interesting, of course, is that because this is another component in hardware, there's actually nothing really special about it in terms of the way Chisel and the way you write Scala code around it behaves, right? We told you, last week to think of, your hardware design as you kind of progressively connecting components. And say, oh yeah, we're just instantiating components and connecting them together. That mentality is still very true with registers, right? You're still instantiating registers, connecting them up. That's all handled. Things like clock and reset, they're implicit. So you actually don't have to pass around the clock signal reset signal all the time. Those are passed through your modules. You've seen those in the Verilog already. Those are already all there. Now, of course, maybe sometimes you want to do something more unusual for your reset or more unusual for your clock, perhaps have multiple clock domains. There are ways to do that in Chisel. You can look it up on the documentation. Cool. And so in terms of, reminding what the functionalities we have, so normally, for register, you have an input, you have an output on the rising, positive edge of a clock. The input is now, loaded into the register, and then from, then onwards, the output is that value. And so every cycle, reads a new input, puts a new output. Now, perhaps you want to have a register, of course, that, has a particular initial value. Well, conceptually, this isn't necessarily the way it'd be done in the circuit, but conceptually, you can imagine it's like having a mux. And oh yeah, if reset's true, we take the initial value we want. Otherwise, we take whatever we're trying to load in. And you know what? Maybe we want a flip-flop that's even more sophisticated, rather than just always writing a new value. We only write a new value if the enable is high, right? So in this case, we take a new value if one is, enable is 1. Otherwise, we keep loading the same old value back in. So this is a little cartoon I draw to kind of show conceptually, how these ports work in a register, but of course, under the covers in actual circuits, it may not be quite written this way. Cool. Questions so far? Great. Okay. Well then, let's actually go ahead and try and write it out. So, as I mentioned before, when we're writing Chisel, we're forced to have things inside of a module. We can't really do. It would be fun to, but unfortunately, we cannot play around with lines without being inside of a module. So here we have a trivial module just so we can instantiate a register, and you can see, really simple, right? We just say, hey, I want a register. In this case, we give it a type, bool, that's 1 bit. Boom, there's a 1-bit register R inside here. So as I said, when we write Chisel, we instantiate things and connect them, right? So we instantiate the register. We connect its input to io.in and its output to io.out. And so if we actually were to go ahead and look at the Verilog we get from this, you can see, yes, if you know Verilog, this is, should, most tools, most of the time, infer a, synchronous flip-flop, right? And so you can see in Verilog, it's a little bit more indirect, right? In Verilog, there's this reg construct, which despite reg seeming similar to register, when you use reg in Verilog, you are not guaranteed to get a register, right? There's plenty of ways to use reg to get this purely combinational logic. Reg is simply a construct that means you're allowed to assign it in certain ways. And whether or not it turns into a register or latch in Verilog depends on how you use it within an always block. And so guess what? All that complexity you may have learned, blocking, non-blocking assignment, all that stuff, not needed for this course. We show you Verilog to kind of show you that this hardware becomes real, right? And you can see, oh yeah, there's, R, it reads from IO in, and it's also assigned to the output. Now, because registers are so commonly used, there's some convenience functions inside of Chisel that let you simplify your register declarations, right? So for example, let's say I want a register that has an initial value. So I could, have a mux and manually do this, or I could just use reg init, and so give it the initial value. And yeah, here we go. So you can see now we're going to see if we're doing reset. If we're doing reset, the value register is going to be hard-coded to 0. Otherwise, take the input. Sure. Cool. But you still see, if you look at the code, we have to, declare the register, connect the input, connect the output. Can we make that simpler? Yes, we can. We can actually use this reg next construct, which declares the register, gives it an initial value, connects the input to this, and then the output of this statement is going to be the output we connect over here. So then return those 3 lines into 1 line. Same functionality, right? Still has a reset signal, still, outputs the output, still has all that, all done in 1 line. It's very convenient. If we want to keep, spiffing up our register, we could also, of course, add an enable signal to it. And it'll reg enable, so it's the same syntax, just you add on an enable field. And yeah, we finally get this. And this one, at first glance, you're saying, wait a second, how does this work? It's snuck in this little else right here. Or sorry, this if right here on if IO enable. And so otherwise, if enable is not true, it's not going to update IO.R. But like I said, it's not course on Verilog, it's a course on Chisel. And you see in Chisel, yeah, whatever you want to do register, we have available, right? We have vanilla register, default value. A lot of times, maybe you find reg next very convenient. But there's nothing wrong with using reg, right? If reg makes sense for you, or especially reg init, those are all great. Cool. Questions? Yes? Yeah, so a good question. So I say register and flip-flop, I've been using them interchangeably. I sometimes think of flip-flop as a single bit, register as a collection of bits, but I'm using them interchangeably. In both cases, they're, synchronous, positive, edge-triggered flip-flops registers. Like I said, if you want to do a latch, you're going to need to use a black box. Yes? Yeah, yeah, exactly. So the interesting bet that was made early on when this was a research language was, oh yeah, modern designs are all synchronous digital. If, super tiny geometries, people aren't doing latches so much anymore. We can get away with, simple positive edge trigger flip-flops. That's mostly been true. The one corner case where they decided, you know what, we really need to have an exception is asynchronous reset. So it turns out in a lot of industrial designs and real chips, there's still synchronously updated registers, still synchronous edge-triggered flip-flops. However, their reset is asynchronous, right? There's a few reasons for that. Number one, Uh, if you have registers involved in your circuit that are involved in bringing up your entire chip when it's first turning on, you may not have a clock yet. You may even need these registers to make the clock. And so, yeah, having registers that can reset asynchronously is important. Additionally, sometimes they may be a touch smaller or even faster. And so there's a reason why people are excited about them. And so, yes, I can go back a slide. There is asynchronous reset flip-flops inside Chisel. So that actually is there. It's not a super complicated lift. Like I said, also if you want to have multiple clock domains, also okay. For the most part, when you write Chisel code, especially in this course, as you see, right, we don't see us talking about clock. And the reason why is that these are all in the same clock domain. The clock signal comes in through this module automatically. It's connected. So there is a clock. It's just we don't need to see it because it's the same most of the time. And it's only if you have different clock domains you actually have to worry about seeing it. Cool. Other questions? Cool. Okay. So let's put this reg to work, right? So we're gonna go ahead and build a counter, right? So a counter is a component where, we have an output, which is some number of bits, which counts the value, tells what number we are, and it's gonna go, 0, 1, 2, 3, up to n minus 1, and then, loop back around to 0. In our case, we'll have a little bit spiffier of a counter. We'll have an enable signal. So that way we can, tell it when to count or not to count. So using everything we've covered so far, here is an example of actually trying to write the counter out. So first off, let's set the IO. Well, we have the enable signal. Okay, it's a 1-bit input. The output is a uint for the count, and we actually didn't set the width. We'll come back to that in a second. We're going to trust the width inference. For the actual count, we're going to store it on a register. Now, one of the interesting things about register, right, is you're going to want to figure out how many bits you want, right? And so in this case, what we're going to do, there's a little complicated stuff here to talk about. We're going to set the width such that there's enough bits to cover whatever value we want to have, right? And so if you do some back-end math on this, right, let's say I want to make a counter that goes up to a maximum value of 7, right? So it's 0 to 7. So the maximum value is 7. If you count 0, that's 8 different things you're representing. And so to figure out how many bits you need for that, well, you got to take the log base 2 of that number, right? So log base 2 of 8 is 3. So yes, 3 bits is sufficient to have a counter from 0 to 7. There is this function available to you inside the Chisel world called log2ceil or log2ceiling. So in other words, it takes the log base 2, rounds up. In that case, let's say, so you can see as we play some more, it'll kind of figure the right thing. But all that complexity aside, what this is doing is it says, you know what, we're going to make a register of uint, and we'll make the width big enough to handle the max value, right? That's kind of what we're trying to do. Okay, given that, what do? Well, what's our next value? If we're below the maximum, we should add 1, right? And if we are at the maximum, we want to know what the next value is, well, we're going to wrap around back to 0. Notice how, for example, these values are .u for uint, because these are Chisel literals, right? We just want to be numeric literals. So that's what the next value should be. Now, that just says the next value should be computationally, but it depends on whether or not we're applying enable or not. So if we're actually using the enable, right, if the enable is true, then we're going to increment. If the enable is not true, then of course we're going to keep the same value. And then we kind of wire it up, right? We say, okay, hey, we will reset this thing. This is doing reset without using the reg in it. We'll fix that in a second. You, of course, can set to 0 or take the output as mux, and then finally connect the output to IOT it out. So this is functional code. And in a few minutes, in the next few slides, we're going to show other ways to write this Chisel. It's going to have essentially the exact same functionality. If the Verilog differs slightly, which it might, it may not be significant, and it may actually, up to the tool's optimization behind the scenes, produce actually exactly the same hardware, right? So, but cool. So this is for us getting started conceptually. So how are we doing? Questions? Yes. Oh, fantastic question. So here for next val, I'm doing a mux to do the wraparound, but hey, if I had a truncating addition, wouldn't it wrap around naturally? The answer is yes, it would if I'm doing powers of 2. So if I want to count to 10, I need to wrap around and make sure it doesn't get to 11. And so that's the key case, right? And so in today's lecture, we're going to see multiple flavors of counter written manually by us. If you go digging in the Chisel standard library, you'll find that counters are included. And after this week, you should use the library counters, and we'll come back to that in a few lectures. Look under the hood of those counters, they're optimized, right? It's a library counter. They want to make sure it's optimized. So they actually have that check. They say, you know what? Hey, is this a power 2 or not? And because of that, they can help make the hardware a little bit more efficient in those cases. So it's one of the cool things about generators, right? Is that we can have this nice abstraction like saying, hey, here's a counter. User just says, oh, I want a counter. I want a certain maximum value. And your generator under the hood can be smart to say, you know what? I'm going to use this organization versus that organization to take advantage of it, right? So this is kind of the fun part of generators. You can say, you can optimize things. But yes, for powers 2, that totally will work. Cool. So actually, while we're playing with this code, let's appreciate it, right? So right now we have the maximum value is 15. That's going to only require 4 bits. So we have a 4-bit counter. All cool. Now, of course, if we went one smaller, we would still have the exact same situation. Now, if we went one bigger, right, then we're going to wrap over and get another bit, right? Cool. Okay, so like I said, this is purely functional code, but we're going to try and use some of the features to make this a little bit cleaner and easier to write, easier to read. Oops, that's not the right place. Let's save that in advance. Okay, so on this prior slide, I want to emphasize, we did the reset manually from mux, right? But hey, no reason to do that. Let's just use reginit, right? So hey, we're reginit. We can pull that in there. So remember, when you give reginit, you need to give the original value for register. If you said 0, which would be a very reasonable thing to say, the if is unspecified. And guess what? How many bits do you represent 0? 0, right? And so it's not going to infer the right width. And so we have to give a little bit of help when we give it the original width here. It's the same math we had from a second ago. Then in terms of the rest of the stuff, right, next val, yeah, we still do the counting and the wraparound, and we use the enable to kind of see that, connect the output. So this should be just about exactly the same Verilog. Perhaps if we go back and forth, we can even see if it's any differences. I'm not sure I can see any differences. There might be small differences in terms of how it labels intermediate variables, but like I said, these are not functional differences that post-synthesis are going to be anything different. Cool. Okay, so like I said, we got rid of a line of complexity, right? That whole other mux reset, using the reginit helpers, tied it up for us. That was nice. Let's keep going. Let's keep tidying things up. You can see here, for example, we have it's applying of the enable manually. So why don't we use the register to help us with that, right? Actually, no, before we do that, let's use when. So instead of muxes, sometimes people find, mux here, perfectly functional hardware. Maybe sometimes people find when more intuitive, right? So hey, when, enable, hey, if I'm below the maximum value, just add 1. Otherwise, wrap around, right? Maybe this is more clear. Yes? Yes, exactly. So the structure I have in this counter right now is, you're right, 2 muxes cascaded. And there are other constructs available in the standard library. There is a mux case. There used to be a mux then. I'm actually not sure if it's available in the current version we have Chisel right now, but yes, good question. But I don't know. For example, even if you maybe didn't come from Chisel before, some might still argue this when structure might be a little bit more clear, right? And like I said, in terms of how this maps to hardware, this is still the same stuff, right? When's turned into muxes. And so yeah, this is perhaps more clear. And now that we, even though we have the when structure, let's see if we can't get rid of this IO enable by using the reg enable. And guess what? The whole thing can be collapsed into one line, right? So we have this mux handling the wraparound, reg enable for everything. Here's the initial value, here's the enable. We did it all in one freaking line. And guess what? It's the same freaking code. So if you're sitting there, staring at it kind of densely, that's why I kind of hint on the slide, right? In my opinion, this is perhaps, although the shortest in terms of lines of code, this isn't necessarily the best most friendly code, right? It's pretty dense. It's a pretty complicated line. You can always, in Chisel or especially in Scala, write really complicated lines to get a lot done, but having fewer lines but are really complicated lines, I'm not sure you've made progress, right? And so personally, my own style taste, I kind of prefer this one, right? If I go, sorry, let me go back a slide. I prefer this one, right? I prefer to have, I think the one structure makes it really clear, right? Okay, if I'm having IO enable, etc., kind of plays out. Cool. Questions? Okay. So, as I said, the standard library includes a counter. So today's lecture is an example of illustrative, but you might, usually use the built-in library counter. And we'll have some examples of that in future lectures. But let's say we want to go ahead and test this thing out, right? So I wrote an arbitrary test case. Nothing super spiffy. You can imagine, hey, we set the enable to 1. So the first cycle we expect it to be 0. There is a new keyword now, clock.step. This is how you advance time in a tester, in a test bed. So we go forward by 1 cycle. Okay, hey, if the enable is still 1, a cycle later it should be 1, yeah. The enable is still true, a cycle later it should be 2, yes. If we turn off the enable, it's 3. And I say, wait a second, wasn't the enable on? Why is it 3? This is from the prior cycle. So the prior cycle enable was on, so it advanced from 2 to 3. This poke is kind of in a way for like the future cycle, and so that's why it's going to stay at 3 for 2 in a row, and then turn it on again, and it advances and even wraps around. And by virtue of us not seeing anything going on here, we see the result, that means it passed. Like I said, if I was to change one of these, you'll see it tell us, oh, no, you got 1 when you should have got 0. Or sorry, you got 0 when you should have got 1. But actually, it should have been 0. Yes, question. Yes, so that's the commented outline right here. And we're gonna come back to the end of the lecture. So we're gonna show you how to get waveforms at the end of the lecture. But yeah, so for now we're doing this style of testing. But yeah, definitely waveforms will be part of the story. Yes. Oh, great question. So how can I, make this less copy paste? So yes, you can advance by multiple cycles by putting a number inside the step parameter, right? So you can say, 2, which would be by 2 cycles. So by default, it's kind of step 1. Additionally, you can use Scala code to actually call these things, right? So rather than having, line, a bunch of stuff, manually writing it out, you can have things like for loops or function calls, whatever you want to do to kind of structure your code to do the right things. Just in the same way, we can write Chisel code where we, use Scala code to structure when we instantiate connect things. You can write more sophisticated testers that, repeat things so it's not so repetitive and manual and error prone. You can imagine you write books on how do you test a sequential element to make sure you're sure it's right. But this is an example interaction of, talking to a counter. Yes. Yes and yes. So yes, there's a version of formal verification in Chisel, and yes, that'll be covered later in the course. So yeah, that's one of the cool things I've been adding in the last couple of years at Chisel. It's been spearheaded by a graduate student at UC Berkeley named Kevin LaFleur. He's even guest lectured in this course in some prior offerings. And yeah, so there is, you can do some assertions that are formally proven. You need a backend for those. If you look carefully, you may notice in some of the binary instances, there's like Z3 being installed. That's why. So you actually can formally prove that kind of stuff. But we'll come to formal towards the tail end of the structured portion of this course. Cool. Great questions. Okay, so then let's keep making our code a little cleaner. How about enums or enumerations, right? So the reason why we're covering these is we're going to use them in a second for a state machine, right? So if you have a state machine, you have multiple states. It may be kind of very tedious to remember, okay, state 1 is this, state 2 is this, state 3 is this. Wouldn't it be nice to have enums to kind of label those states? That's what we're going to cover with these, right? So there was a prior way of doing this in Chisel. We've followed a new language and is using what's called chiseling in a much nicer way. So for now, you use kind of this boilerplate syntax. It'll become less surprising as you get more familiar with the language in the coming weeks. But basically, name your enum, give values you want to, give names for the enumerated fields you want, and then it's going to go ahead and turn these into uints, right? So, for example, here I have created it. If I want to know, hey, what is name.a? It's 0. I could print out more things. to see, how they all are assigned. You can say, yeah, it's, 0, 1, 2. I think it was a question, yes. So I should clarify, right? So this is, a newer one. The old one, I'm not sure is even deprecated. Maybe it's deprecated. I don't know, but um, there's nothing wrong with it. It just had different syntax. If you look at the Git history of this repo, you can see the commit made in the last 24 hours to modernize from the old enum to the new enum, and you can decide side by side what syntax you like. Um, there are some nice things to the newer one. Something that makes the syntax a little cleaner. It has a little bit stronger typing, so you can kind of get more security out of it. There are some corner cases where the old enums didn't quite give you the kind of stability you wanted, versus these newer enums do. And so, yeah, so there's actually pretty spiffy documentation provided. So if you click on this link and then go to the next tab, you can see, yeah, here we have these docs kind of having a nice casual conversation about how it works. These docs tend to be really well written by the Chisel developers. They have a setup where these code snippets are actually compiled and run. So there tends to be very few bugs in these things because they actually are doing continuous integration on their documentation code examples. And you can see for a lot of these built-in things, you may find this cookbook very helpful, right? So these explanations or cookbooks, depending on what you're trying to do. Cool. Other questions so far? So by default with enum, it's actually, sorry, I should say chisel enum, you just say value and it assigns things. Here you put them all in one line. It'd be very compact. You can just as well, put it on 2 lines, and now I have yet another enum that's been assigned. What's interesting is you're also not required to take a default value, right? Maybe you want a certain value. Let's say I want it to be 5. Oops, that's going to yell at me because it's the wrong type. You even learn to parse messages together, right? I gave it an int, that's a Scala type. It wants a chisel uint, right? A chisel type. So hey, guess what? I got to put a .u on there. Now it works. You can see, oh yeah, because I manually specified I wanted a certain value for one of these enumerated types, there's a gap now in the range, right? But the point is, at the end of the day, enumerated type is just a fancy way to have names that correspond to numbers, and just you want the numbers to be unique, so that way you can have things work. So basically, the hardware is going to have numbers, right? Hardware is going to have a uint in the circuitry. However, we want nice names for us writing code as humans. And what's cool is from now on, demo enum is like a type. We can basically use it, say, hey, I want something of this type, and you'll have that kind of type checking. So for example, let's say, I'll show that example in a second with the state machine example. If I was to change things that should be enum to not be enum, it'll tell me, no, you're connecting things that don't match in type. So it'll warn you, so it expects the type. So that's one of the nicer things about this newer chisel enum is it actually gets the typing right. Other questions so far? Cool. Okay, let's go ahead and put it to work in a state machine. So first off, what is our state machine? Well, let's say, we're going to take one of our, local residents here in Santa Cruz, the raccoon, and you were trying to characterize this behavior. Well, you have some initial state. Let's say it's initially hiding. If it doesn't hear any noise, it's going to go to wandering, right? It's the wandering state, the wandering action. Perhaps eventually it finds trash. Great. It's going to rummage through the trash. If it finds food, it can eat the food. Of course, if it hears noise, it's going to go back to hiding. At any point, right? If it's wandering, here's noise, hides. If it's rummaging, here's noise, hides. If it's eating, here's noise, hides. Now imagine maybe it finishes the food, it goes back to wandering and find more food. Cute example state machine, 4 states. Okay. Let's code this up, right? So let's talk our way through it. So first off, we're going to have an enum for the states. And so the state machine, the states and the actions are kind of the same thing, right? If we go back a slide, oops. Go back a slide, right? You can see hiding is both the state of being in hiding as well as the action of hiding. So yeah, I made this enum rack action, raccoon action, hide, wander, rummage, eat. Those match those states in the prior slide. The actual module here has inputs for noise, trash, and food, like we just saw in the prior, thing. These are the labels and the arcs. These are the inputs from the system. The output of our system, of course, is the current action or the state. Okay, so how do we set this up? Well, initial state is going to be, we're taking advantage of that reg initialization to be hiding, right? So you can access that, by using the hide. And then we have a bunch of whens here. Okay, if I'm in the hiding state and there's no noise, then I can go ahead and connect state to wander, right? Now, one thing I want to point out here is notice how in the state machine, I'm checking state and connecting state. There's no next state variable like you might write in some languages like Verilog. And what's interesting about this is actually it's all going to work just fine, right? The reason why is state is pointing to this register, right? So this register has both an output and an input, right? So when I do like when state equals, remember we use triple equals and chisel, I'm checking the output of state. So what does the output of state look like? I can see, is it this enumerated type? Is it this other enumerated type, etc. I can do comparisons on the output. This line, because state's now on the other side of the connection operator, I'm now changing what the input of state is connected to. That's why it's totally fine to not have the next state, because it's a register. I've connected it to, this particular literal, in this case, enumerated value. And so I connected the input to that. And so then when the clock cycle terminates, the next clock cycle starts, and take that value. And so this is kind of a very direct way of writing it. You don't have to kind of keep having state, next state, etc. It's just all state. And remember, state is a register in this case. And we're just changing, comparing the output with these when statements. And then we're changing what the input is connected to over here. And we'll see when we write the Verilog in a second. But yeah, all these combinations of whens and these changes of state, there's a bunch of muxes, right? That's going to happen. But that's kind of key thing. So you can trust, hopefully I converted that, diagram faithfully into a combination of whens. You can see it's often, nested whens. If I'm in, wander, if there's noise, I do one thing. If there's trash, another thing. So go back a state. Oops. Looking at the state machine, if you were to be a, state machine purist, you would know, yeah, wait a second. In wander, there is both noise and trash as exiting edges. What if noise and trash are true at the same time? That's something underspecified. Yeah, it is. But I chose, when I made this, to make noise, be the dominant one. So thus, if there's any noise, that is the case. And if there's not noise, then you care about there's trash. But cool. So here's kind of, very little description of that state machine. We output the action. So go ahead and print out the Verilog. It's going to be kind of tiny at the bottom of the screen. But you see there's a lot of stuff going on here, right? For example, there are these various muxes that kind of correspond inside these state arcs. And then, there's a bunch of if statements for the various cases. You can see it's checking the current state. And notice how in my code I had an enumerated type. But of course, in real hardware, we need to have actual numbers, state 2, state 1, 2, 0, etc. Cool. Questions? Yes? As opposed to? Sorry, say it again? Oh, yes. Yeah. So radar in binary is going to be basically just consecutively increasing. But remember, with the enum, you can assign the values you want, right? And so actually, one of the examples, if I still have the tab open, there's actually a really nice example I like in here they stole from the processor, which is, hey, you know what? Let's say I want to build a decoder for my processor. I can put the opcodes as enums. This is actually pretty cool, right? So basically, if it's a load, IPC, the various instruction opcodes. So then later on, you can go ahead and have your processor actually use those opcodes. So there's an additional example that actually uses the opcodes and matches based on them, right? And so it's actually a pretty cool example they built, right? So you see the example is converting it. You can grab it. You can cast it. But yeah, that's pretty neat. So you basically can, like I said, they're not required to be contiguous, right, or consecutive. But if you don't assign them, they will be consecutive. Cool. Other questions? So let's go back to that thing I was talking about a second ago about the typing, right? So if we're paying close attention, we'll note that this register is actually of the type required to hold this enum, while the output's a uint, right? So what does that mean? Well, these are different types. So to make the enum a uint, you can call dot as uint to make it do the cast to get the uint value out. If I was to remove this, it's actually going to break it. And the reason why is the types don't match. Now, this is a situation that, we were just talking about before lecture. Maybe we'll spend a minute helping folks debug. So notice how Jupyter here is, showing a asterisk, meaning it's running. It's actually not running. There's been an exception. But the exception is not being printed here. So what can we do? Well, if you're running locally, this is not available in Binder, unfortunately. You can pull up your place where you're running Jupyter from, and you can scroll back and see the console log, what's going on, and you can see, oh, wait, that was not the error. Here's the error. Exception user code is trying to connect things, right? And says, hey, wait a second. I have a uint and a rack action, and these are different types, right? And so they're not compatible. So to fix that error, oops, let's get the thing back. What can I do? I can do a few things, right? I can, put it back to like this as before. I can even tab complete that. Or perhaps maybe it's better to embrace the enum and go from there. Oops, I need to give it those, right? And that also works. Cool. Questions? Oh, good question. So why does it hang sometimes versus getting an error message? So it depends on where the issue arises in the language. So it's one of the challenges of making an embedded language like Chisel, which is embedded inside Scala, is when something goes wrong, communicating very clearly to the user what's going on. And that's actually been a lot of the work by developers for years now, is how do they structure their code to make it give the most intelligent information back to the user. In terms of actually it's implemented, some things that are in the toolflow process that goes through your code are actually exceptions, right? So an exception is what's happened there, and that's why this Jupyter environment is not a case of using Scala or Chisel normally, but this Jupyter environment made for this course, which is a little bit of a hack. The exceptions has that behavior, and so things that allow the code to terminate normally, but with an error, you'll see the red printed out. Things that cause an exception and the print terminate normally, you will not see the output. Cool. Yes. Yes. Yes, exactly right. So yeah, if I keep this type here, things connecting to that also need to have that type. And that's kind of the point of both Chisel and Scala in general way you're typing is you want to have things be very knowledgeable what the types they're working with, and the types don't match up. You want to tell you, hey, they don't match up. And usually humans should figure out, okay, well, I should change this one, or perhaps I should do a cast, etc. Like I said, when you write C, it's like very permissive, right? You can have, it's like int, this is a long, UN64, whatever, they're all okay. Here it's like, no. These need to be the same. And if they're not the same, it tells you need to fix it, right? That's kind of the whole point. Cool. Okay, so this example, we are using the when statement, which we've seen. We know when, we like when, we can do when, an else case, else when, etc. You may be wondering, well, this seems pretty dense. Is there a chisel switch? Yes, there is a chisel switch. So if I go forward, here we go. So now, this is very common for state machines. Maybe we have a number of states. We can switch on the state. And yeah, based on what state we're in, we take actions and say, here's the same, logic. Actually, inside of these switches, we're actually choosing to use whens. That's totally fine to mix and match these. This will, like before, produce basically the same Verilog. It all comes out. Cool. So yeah, so switch you may find more convenient. When's kind of an all-purpose one. Switch is kind of a special case of that cascading sequence of things, but you can make your code a little tighter, especially for state machines. Yes? So I'm not familiar with BlueSpec state machine library, but no, there's not, to my knowledge, a state machine builder inside of Chisel. One of the things that's interesting is when you start really imbibing the Agile hard design philosophy in Chisel, you have state machines, but they tend to be more implicit and simpler. I think a lot of times when we spend a lot of time, drawing like, transition diagrams and having really clear arcs and that kind of stuff, that's kind of a bit more of a waterfall style philosophy. Sometimes you have a much more kind of implicit state machine with the Agile philosophy. But for sake today, I'm covering the kind of the more classic rigid state machines for a few reasons. Number one, Agile or not, we still use them all the time. Number two, it's also a great way to kind of show the things we're covering, right? We're showing using registers, using switch, using enums. It kind of covers a lot of things together in a kind of a nice, integrated, motivating example. Now, to your point about what if we had some sort of helper for state machines, yeah, I've always wondered about that. That might be an interesting thing to consider, perhaps even for project later in this course. Maybe you want to make some sort of generator that takes in some sort of description language of a state machine and actually generates a state machine for you. So perhaps some person could write, some sort of simplified syntax to describe these arrows, and then you turn it into a state machine for them or something. Okay, sure. From which ones? So what's the property that's wrong with this edge? Is because it's a cycle? So this is cyclic. So it wants to be acyclic is the constraint, or okay. Yeah, so it said these are the kind of challenges you come up with if you were to make, for example, a state machine generator as a product potentially. Um, but yeah, so this is an example of a state machine. And it's very common. You're building a module and you have like two or three states, right? And based on two or three states, you kind of do something. Rather than always having such formal arcs and arrows, you might just have, most of the code behaves the same independent of the state you're in. And a handful of places, depending on what state you're in, maybe in those places you have a when statement or a mux to do the right thing. But like I said, it's still a good example for today to kind of cover all these things working together. Cool. Okay. So I, you know, wrote out a manual sequence that actually runs through those states. Um, if you're looking at this saying, oh my gosh, this is really, really hard to parse, you're not alone. Uh, One thing you can do and take advantage of, let's say, for example, uh, let's go back to this one, make this the active one. So now output is rack action rather than on the next one, which is uint. So these types are, I think, going to not match anymore, right? Hey, I'm expecting a rack action and you're giving me uints. Let's go ahead and change it over, right? Make our test case a touch more understandable if, we were to, for example, use the enum, right? Um, and you know what? I'm a little bit too lazy to change all of them right now. So we'll just settle for changing some of them and watch improving compiles. But yeah, so you can see that, for example, the enums are making our life nicer, right? So the old enum, you kind of had that case, you had to import it. In this new case, yeah, more verbose, more descriptive. That's nice. Cool. Um, so back to the point asked half an hour ago. What can we get out of simulation? Well, I just showed an example using ppoke tester, and they said the tests aren't super exciting. If everything goes right, nothing happens, right? It's only and it only yells at you when something fails. Um, but despite that, tests are really the kind of way you want things to work, right? You want to have tests, you want to have automated checking of things. Um, that's a good thing. The only downside to tests is sometimes they aren't quite as helpful as you would like when you're developing, right? It's one thing when you have the module is complete and you want to make sure it still works. But when you're developing, you kind of want to see what's going on, right? And so for debugging, developing, you want to see what's going on. You have two choices, right? You can use a waveform or you can use print statements to print out certain things. Now, every quarter, I always am reluctant to teach people about prints. Sometimes people get too attached to prints. There's a certain point in hardware design where you should abandon prints and use waveforms. For those from the software community who may not have much familiar with waveforms, they're actually really amazing. It's kind of like you get the value of all of your signals for all time, right? So there's no need to run it once, realize you need more data, and run it again. No, you just run it once and spend a lot of time looking at the waveform, and then one go you figure out the bug and you go fix it. With prints, you often put some prints in there, you see some value, oh, I should take this other case and write some more prints, and it kind of pulls you in. It's like this like slow downhill stuff pulling you down, right? You do like one small thing, oh, that's easy, and you kind of keep doing more and more prints, and then half an hour later you have 10 print statements, right? And so we're going to show both, and so we'll just kind of trade offs for both, right? And so let's go ahead and try some prints, right? Sorry, before I finish, I want to belabor one philosophy point here, right? For real designs, you want to actually get put in the hardware you actually, use in your daily life. You want to work, right? Things that work, you want to have automated tests that are good tests. Tests should be the common case. Tests should be the final deliverable case. Waveforms and printing are only for debugging. You do not want to get a repo from somebody that says, hey, that's my module. You say, oh yeah, what about a test? Oh yeah, run that test and then make sure that text in the print matches this text. It's like, what are you talking about, right? Like, you don't want that, right? Like, but this happens when you're developing, right? You're developing on the fly, you do this, and then say, you know what? You did that on the fly. You're then going to fix that and tie it up and revise it and make it better, use the test, right? So, like I said, prints and waveforms are for debugging or development, but they're not the way to do testing. Testing, you should actually use tests to make sure it does the right thing. And in general, in debugging, I recommend waveforms. There's a touch of friction for some people. Oh, yeah, I don't know if I set it up. I know many of you love VS Code. There's a waveform plugin for VS Code. Use that. I linked to it from the homepage. Get your waveforms on. Okay, so we're going to do prints first because next in slide order, and then we'll come back to waveforms at the very end. And we're doing great on time. Okay, so for printing, Scala has its own print line function. Built in, prints the system console. Nothing too crazy. It has string interpolation as well. So you can take variables from your environment and by putting a dollar sign in front of it, replaces that with the value, right? So for example, hey, my val is 4, so it replaces my val with 4. If you want to actually call a function or something, you can do that inside of the print string if you put it inside the dollar curly braces, right? And here in this case, I'm calling .getClass just to do something. You can do, arbitrary things, right? But yeah, so this is just Scala. It's not even Chisel. This is Scala. You have, strings and you have string interpolation. If you are familiar with Python, it's F strings. F strings in Python are Python string interpolation. And those were added in a couple years ago. So yeah, this is a kind of pretty cool feature. It's nice and handy. So why might you use this? Well, you can see from the title of the slide reminding you that, remember your Chisel design is a valid Scala program. And so while it's running, you may want to print out various things for you as a user, especially the developer, to see what's going on. Oh yeah, I know I inferred this should be this big, or recognize my counter that the maximum value requested is such due to the power of 2 optimization I talked about, right? And you can have those kind of prints and that kind of stuff. Okay. What about in Chisel? Well, Chisel provides 2 print statements. Remember, to remind ourselves what these prints are for. These prints are prints that are triggered in simulation, right? They're not going to go into real hardware. If you push these through a CAD flow, they're going to vanish, right? They're actually in that case like the prints in Verilog, right? They're only simulation only. So you can do two ways, right? So in both cases is printf. So printf's a Chisel word, not a Scala word. You can do it like really classic vanilla printf, where you have your format string and then separated by commas all the arguments to fill in, the places where you have the format things, %d, %u, that kind of stuff. That isn't really my favorite. I tend to like to do it interpolation style, where you, in this case, rather than being S, which is normally the case for Scala, if I go back a slide, for Chisel, you use P for printf for the interpolation. Yeah, I'll interpolate the right thing. So you might say, okay, if I like interpolation style, why in the heck did I bother showing the old school printf style? The reason why is if you have a really, really carefully made printf, sometimes you want to have like very specific formatting. I don't know if you've ever done this in printf, where you can put like numbers to like set the exact widths of things and the precisions of things. That's done better to format string. If you aren't doing any advanced formatting, do interpolation. That's kind of easier way of doing it. And yeah, for example, let's say here's our counter from before, except for now I added 2 printfs, right? Hey, what am I incrementing to? And I mentioned I'm wrapping around, right? And yeah, if I go ahead and run this, it just redefined my counters now inside the, memory of this JVM. It says, oh yeah, my counter corresponds to this version. But yeah, I've added in these printfs. If I go forward a slide, and now I run the test, you can see, yes, here it goes. So, it runs multiple cycles, and we can see it prints out. So in the case of a print statement, let's be really clear about this. The print statement is evaluated every clock cycle. So if you have combinational logic and you keep changing inputs to it, like for example with poke, and it's purely combinational logic, the outputs, if you do peek or expect, will change correctly. The printf will not be called. It's only be called once per cycle, right? So if you do tons of combinational tests, but you never advance time of a clock cycle, you only get one print statement. So sometimes students have this, confusion, like, wait a second, I do a print statement and I have no way to change my value, but I can't see it, right? That's why. It's because it only does the printf evaluation once per cycle. But that's cool. Following on the request from earlier in this lecture, we of course could simplify this to be like that, right? No problem. Cool. I see a question. If you go back a slide, you may notice I had two forwards to that printf. Here I have the format string style. We could do instead the interpolation style. It has no impact on the output, personal preference, that kind of stuff. Okay, so then, actually before I do literals, I'm gonna go back and let's do waveforms. So how do we get waveforms? Well, if we go back to our earlier counter test, I can say, hey, why don't you write the waveform? So this is a little bit clunky syntax, but yes, you can basically say, write the VCD. And it did that. Now you may be saying to yourself, okay, where is that VCD? That VCD is lurking inside the directory. So let's go ahead and pull up the console and see what we're doing. So here I'm in lectures. We're lecturing from lecture 4 today. So make it even bigger. So okay, what's inside here? Well, it turns out when you're running these commands, it's actually, producing files. So for example, things like in the raccoon, we can see, oh yeah, there's the Verilog file it made, right? We talked about some of these other file formats, for example, the .fir. That's that intermediate fertile format. So this is, the internals. This is the chisel front end made for something else later on to go process. What is this ano.json? That's going to show us the various aspects of the tools. As a user, you probably never need to look at this, but you can kind of see the various passes that are being run to the tool. But the one that matters for this particular conversation about the waveforms is this test run directory. So we go to test run directory. Every time I do an execution that produces something, especially a waveform, you're going to get this. So these are all time-stamped by when they're run. So I believe this should be the newest one. Let's hope it is. And yeah, there's our VCD. So what did the VCD? How do I visualize the VCD? There's a few choices, right? So if I go back to the course homepage, under tools, I added some links here to various VCD viewers, right? So there's a few of them, right? GTK Wave is the classic one that's available everywhere. There is something called Scansion for Mac OS, which is no longer supported, but still runs Snapple Silicon, so I'm still rocking it. For those of you with VS Code, something called Wavetrace. And there's even a web-based one we'll show in a second. So I'll kind of just show them all, right? Let's see what people like. So maybe first, let's go ahead and use Scansion. Here I'm on the Mac and say I kind of like Scansion. Let's show that. So I find it easy sometimes to get direct access to the waveform. Go ahead and pull up Scansion. Now I need to open a waveform. Let's say I want to open that one up. And yeah, here I go. I have a waveform, right? So look, right now, of course, there's no waves. I need to add them in. Let's say I want to see clock and reset. There we go. I can auto zoom it. Can look at the enable. If the enable is on or off at certain times, count. We've seen waveforms, right? And this is pretty cool, right? So we can kind of see what's going on. No reason to keep doing tons of prints. Even that print example I had, I only printed so much, right? And so you can imagine maybe you want to print more variables and you keep changing your printf and running again and again. Don't do that. use the waveform, right? That'll make your life happier. Like I said, the most common way people do this is often with uh, um, GTK Wave. So actually, I've already loaded up a GTK Wave instance. In this case, it's actually running on a server because I don't have GTK Wave installed on this Mac. But yeah, it's the same file we're just talking about. You can drag in your clock. You can see your reset. You can see the output over time. You can change, I want the data to be viewed as decimal rather than binary. Yeah, no problem. Waveforms are pretty awesome. And then, like I said, after all this, you're saying, you know what, I really, really want a waveform, but I can't use the ones I was telling you about. Well, there's the default one, or not the default, the backup one, if you want to think of it, is that. And that is this one, right? There's literally a web page. Go ahead and open it up real quick, where you can simply just drag a VCD file there. This is maybe one to folks in sci-fi, and voila, you get waveforms. So waveforms are everywhere. Perhaps the question you're wondering is, this all is great. How do I get waveforms in my Jupyter? I tried to make that a thing last quarter or last year. I didn't quite succeed. If you go digging around inside the source code, you can find it where there is a way to generate a waveform, taking the code from this web page to actually render inside the Jupyter. I found the results unaesthetically pleasing. It was kind of an odd aspect ratio, weird font sizes, etc. Perhaps one of you is more JavaScript talented and can help fix that. That'd be appreciated. But yeah, so like I said, if you're working, for example, on the labs in Binder, you can download your VCD file and then drag into this browser window to get that web version. But this is more important for the homework, so we have like bigger, longer, harder problems. There, you should definitely figure out a way to get waveforms going. GTK Wave, the one for wave trace is one for VS Code, Scansion, etc., whatever you're using. Really, really recommended. One of the things I did, I guess 2 offerings ago, is I turned on waveforms by default for the homework assignments. Waveform usage jumps dramatically. So, right, as soon as you're sometimes in short turn on waveforms, I put it on by default. So go dig around in test run directories, you'll find it. If you find it confusing to keep having to figure out which is the most recent test run directory, there's a way to get it to hard code the output directory, and if you run multiple times, it overwrites it, which sometimes reading waveforms makes life easier. Cool. Questions on waveforms? Cool. Okay, well then let's get back to lecture then. So then the final point was just some convenient stuff about numbers, right? If you are working with numbers in Chisel, right? You've seen us, casting things with .us, .s, .b for bool. That's fine. But you may want to have, longer literals, right? So what can you do? Well, you can do things like actually using a string and then casting that to a uint, right? And if you do a string, it knows you want, if you say H, you can get hex. You can do octal, you can do binary, so if you want certain things. So you can see it's kind of like a map to various things. Maybe I want to even do, binary. Sure, that's fine. This is handy, right? So you can do underscores, you can do strings to get hex, break it up. You can give the widths explicitly if you want to. Otherwise, it infers it. So for example, for A in hex, that's 10. You need at least 4 bits to represent that. So that's what it infers. You can say, you know what I want for sure, 8 bits. Yeah, you got it. Instead of .u, you can say .as uint. This is kind of more in the flavor of how Scala does things. And most of Scala conversions are like .as something. But, .u is nice and short to use a lot for Chisel. Cool. Any more concluding questions? Cool. Okay. Well, that's that. Thanks for everyone turning in Lab 1 last night. That was our first assignment. We have homework 1 due this Friday. And then we'll be posting another lab probably tomorrow, which we do next at the end of the week. And we'll kind of keep going from there. Cool. Welcome. All right. That's all, folks.